Hello and welcome to the Embedded Online Conference. My name is Miro Samek and this is part 3 of my presentation, Modern Embedded Software Goes Beyond the RTOS. Alright, this was a lot of dry theory. So now let's actually see how active objects could be implemented, first on top of a traditional RTOS and later with a dedicated active object framework. Starting basically from the previous sequentially coded blinky button example with FreeRTOS, now you need to add the active object services. Because the active object layer will be based on FreeRTOS, let's call it FreeAct. The minimal implementation of FreeAct will consist of the FreeAct.h header file and the FreeAct.c source file. The header file begins with the event facilities. The event signal will be just a small integer, which will hold enumerated signals representing various interesting occurrences in your application. There will be a couple of reserved signals, such as the init signal, that will be dispatched to each active object right before entering the event loop. The user signal will be the first signal available to the users. Next, you need to define the event structure. It needs to contain the signal, but it also needs to be extensible to fit arbitrary event parameters. This would be accomplished by the object-oriented concept of inheritance. If OOP in C is new to you, I would recommend to watch Object-Oriented Programming segment of lessons in my YouTube video course. But here, just to give you an example use case, a hypothetical Ethernet event could inherit the event-based structure and could add the Ethernet packet as the parameter. The C language standard guarantees that the first inherited member, super, will be always aligned at the start of the derived structure Ethernet packet, so it is always safe to cast a pointer to the derived struct on a pointer to the base struct. This type of casting is called upcasting and is performed automatically in object-oriented languages like C++. Moving on, next you need to define the facilities for active objects. You start with the forward declaration of the active object struct, followed by the definition of the dispatch handler pointer to function. This will be a virtual operation in the active object class. Next, you can define the active object struct, which, as you recall, needs to have a private thread and a private message queue. To support the FreeRTOS static allocation policy, which in my view should be the only one used, you need to provide the memory buffers for the thread and the queue. These are called control blocks in most other RTOSes. Finally, the active struct contains the pointer to its dispatch virtual operation that would be implemented in the subclasses. The specific subclasses of the active base class will also add their private data through inheritance in the same way as subclasses of event add event parameters. You'll see examples of it in a minute. The active object class will have a few public operations, starting with the constructor, which in C is just a regular function that you need to call explicitly. Then, the active start operation will start the internal thread of the active object. And finally, the active post operation will asynchronously post events to the active object. Because of the bizarre design of FreeRTOS, you need to actually provide two variants of this operation, one to be used in the thread level and a separate one to be used in the ISR level. Now let's quickly review the implementation of these services in the FreeAct.c source file. First comes the active object constructor, which simply sets the virtual operation dispatch that in C is implemented with a pointer to function. Next comes the active object event loop function that will be used as the thread function for all active objects in the system. Please note that this function is defined as static, which makes it local to the module because it can be completely hidden from the rest of the application. This event loop implementation is essentially identical to what you just saw a few minutes ago. The only difference now is the dispatching of the initial event to the active object right before entering the forever super loop. Here I'd like to point out one interesting aspect of dispatching the initial event. The chosen active object interface posts actually only pointers to events, not the whole event objects by value. So in general case of mutable events, you must be very careful to precisely control the ownership of such events. But events without parameters can be constant and allocated in RAM. Such immutable events can be shared freely because they don't pose any concurrency risks. You will see a few more examples of posting immutable events later in this quick code review. The ActiveObject start operation creates the FreeRTOS message queue and the FreeRTOS thread. The most important aspect here is that all those threads are based on the same static event loop function. However, the same thread function operates on different ActiveObject instances because you pass the me pointer as the v parameters to the task create FreeRTOS API. This is how the thread routine gets access to the ActiveObject instance me. And finally, you need to code the two variants of the ActiveObject post operation. Both of them delegate to the FreeRTOS xQSend variants, whereas the queue being used here is the private queue member of the ActiveObject class. So this is about it at this point. Now, let's try to use the ActiveObject layer instead of the naked FreeRTOS. For starters, let's convert just one of the traditional sequential threads to an ActiveObject. It turns out that the button thread is easier with the currently available ActiveObject services. You can keep the original sequential code as a reference for now, but remember that most of it will be deleted after you are done. So first, you need to create the button ActiveObject class by inheriting the ActiveBase class as the first member super. The button ActiveObject has no private data, so you don't add any other parameters to the struct. Next, you implement the button dispatch virtual function, in which you process one event at a time. Typically, you base the code on the switch statement, which discriminates based on the event signal. When you receive the button pressed signal, you turn the LED 1 on. When you receive the button released signal, you turn the LED 1 off. All this corresponds to the actions performed by the sequential code, except now, in the event-driven code, you don't block to wait for events. All waiting is separated out and happens at the top of the event loop. The last function you need to define is the constructor of your new button class. Here you have to call the base class constructor, where you attach the specific button dispatch implementation to the virtual dispatch operation. This completes the definition of your new ActiveObject class, so you can delete the reference code. You can also delete the task control block, but you need to keep the stack because it is still needed for the internal thread of the button ActiveObject. Now you can also get rid of the semaphores, but instead you need to provide the memory buffer for the private event queue of the ActiveObject, the instance of the button ActiveObject, and the global pointer to the ActiveObject so that other parts of the code, such as BSP, can post events to it. Speaking of the semaphores, you need to replace the signaling of the semaphores in bsp.c with posting events to the button ActiveObject. The button pressed and button released events have no changing parameters, so you can use the immutable const events in RAM. The last change in main.c is to call the button constructor explicitly and to start the ActiveObject by calling the ActiveStart function. And this is finally all as far as the button ActiveObject is concerned. Please note that the blinky functionality is still coded with the traditional sequential and blocking FreeRTOS thread. I know, you must be hanging by the edge of your seat to see how it all works. So let's just load it to the board and run it. As you can see, the LED 0 blinks as before, but this is hardly surprising because this is still the old sequential code. But the button is the new event-driven ActiveObject code, and as you can see, it also works flawlessly. So congratulations, you just implemented your first ActiveObject. Alright, so now I'm sure you want to go all guns blazing and convert the sequential blinky thread to an ActiveObject as well. Using the button active object as a template, you can just copy and paste that code and replace button with blinky. But now comes the most interesting part, which is the actual implementation of the blinky dispatch operation, where, as you should remember, you are not allowed to use any blocking calls. But herein lies a problem. How do you convert the blocking RTOS delay into an event? I mean, button press and button release were obvious events, but where is an event in the time delay? Well, every blocking call always corresponds to an event, even though initially you might not know how to call it. But time delays specifically correspond to time events. A time event is an event that an active object can request to be posted to its event queue in some time in the future. Such functionality does not yet exist in your FreeAct active object layer, so you need to add it. First, you go to the FreeAct header file, where you add a time event class. Because time events are just specialized events, the time event class inherits event. But in addition, a time event must remember the active object that requested the timeout, and the time event must also keep track of the timeout, which will be a down counter decremented by every system clock tick. When the counter reaches 0, the time event will be posted to the active object, and the time event will be considered disarmed. This also means that the timeout value of 0 indicates a disarmed time event that is not ticking. Finally, often you might want the time event to be delivered periodically. This can be quite easily achieved by adding the interval member. This interval would be loaded to the timeout down counter when it reaches 0. That way, the time event will automatically arm itself and will keep ticking towards the next timeout. The interval value of 0 will then naturally correspond to a one-shot time event that would be automatically disarmed after expiring only once. The time event will have a few public operations, such as the constructor, as well as the arm and disarm operations. Finally, the class-wide operation tick from ISR would be a static class operation without the me pointer for the specific instance. It will service all instances of the time event class every system clock tick. Now, regarding the implementation of the time event operations, I'd recommend the time-honored rule, when in doubt, use brute force. More specifically, to keep track of all time event instances in the system, you can simply use a static array of pointers and a counter. Then, in the time event constructor, you would initialize the data members as usual, but you would also store the time event pointer in your static array, and you would increment the time event counter to register one more time event in the system. The time event arm operation would simply set the timeout and interval members, while the disarm operation would set the timeout to 0. Finally, the most interesting class-wide tick from ISR operation would go over all the registered time event instances. It would first check whether the time event is armed, and if so, it would decrement the time event counter and check again if it just has reached 0. If so, it would post the time event to the active object, and it would reset the timeout counter from the interval data member. This would work for both periodic time events and one-shot time events when the interval is 0. The last modification you should not forget is to add the time event tick from ISR call to the system clock tick FreeRTOS callback so that the registered time events are serviced. Alright, so this was the extension of the active object layer. Now let's use it to implement your blinky AO. This active object clearly uses time events, so let's add one time event instance to its private data. As all private data members, the time event member needs to be initialized in the constructor, where it becomes associated with the active object meSuper and gets the signal timeout defined in bsp.h. So now you have the event signal for your timeout, and you can write a case statement for it. But here comes another problem. Should you turn the LED on or off? I mean, in the sequential code you knew exactly. But here, in the event-driven code, you need to know whether the LED was most recently on or off. This information needs to be stored in such a way that it will survive the calls and returns from the dispatch operation. This means that it definitely cannot live on the stack as an automatic variable. Instead, the ideal place for it is the private data in your ActiveObject class, where you add the isLEDON boolean flag. Assuming that the LED is initially off, you can set the flag accordingly in the constructor. Now, in the timeout case, you first check the flag, and if it indicates that the LED is not on yet, you turn it on and remember this change in the flag. Then you arm your time event to expire in 200 milliseconds. Otherwise, you turn the LED off and set the flag accordingly. Here, you arm the time event to expire in 800 milliseconds. This off time is intentionally different from the on time, so that you will be able to clearly see the difference in the blinking pattern of the LED. And this is all for the blinky class. But you still need to correct a few little things. Clean up the old code. And you need to create the blinky instance and start it as an active object. Now, of course, you need to test the code on the board. And when you start it, the LED 0 definitely does not blink as it should. Because nothing happens in the application, it would be interesting to check whether the time events are being posted. For this, you can set a breakpoint in the tick from ISR function at the active post call. Now, when you reset the target and run again, you never hit your breakpoint. This means that no time events were ever armed. So let's take a look at the blinky dispatch code again. I wonder if you can see the problem. Well, the time event is armed only in the timeout case, but this case executes only when timeout event occurs, so you have a chicken and egg problem. You need to prime the pump, so to speak, and this is exactly where you can take advantage of the init event dispatched to every active object right before entering its event loop. Here you can explicitly turn the LED on, set the isLEDON flag, and arm the time event. But this is just repeating what is happening in the timeout case when the flag is cleared. So your other option is just to intentionally fall through from init to timeout. Alright then, let's apply this fix and try again. This time around, you hit the breakpoint in tick from ISR right away. After you remove the breakpoint and run the code free, you can see that it works as expected. Both the button code and the blinky code, where you see the short pulses of light with longer pauses in between. Now, as the very last exercise, I'd like you to take a critical look at the two active objects you've created. They came to be only because you've translated the sequential design from the conventional RTOS to active objects. But the real and only reason why you ended up with two active objects is that the sequential superloops were not composable due to unresponsiveness. Making them composable again was the whole reason for existence for an RTOS, at the expense of creating threads. But this is no longer the case with event-driven code, which remains responsive to all events. This means that event-driven code is directly composable. Well, in that case, you should be able to merge blinky and button together into just one active object. So let's actually do it right now, starting with renaming blinky to blinky button. Next, you need to move all events handled by button to the blinky button dispatch operation. And then you simply delete the button active object altogether. Note that by doing so, you free up significant RAM for the stack, control blocks, and the queue buffer. Obviously now, you no longer need to create or start the button active object. You still need to do a few name changes to fix the syntax. And finally, as the compiler reminds you, you need to change the global AO button pointer to AO blinky button. Of course, the very last thing to do is to verify that the thing still works as before. And indeed, it does. The LED 0 blinks with the expected duty cycle, and the button turns the LED 1 on and off. So, what have you learned from all this coding? Well, I hope quite a lot, actually. For starters, you just witness a paradigm shift from the traditional sequential programming with blocking to event-driven programming without blocking. This experience gives you, I hope, a new perspective on the traditional sequential programming, because now you understand that every blocking call really corresponds to an event. Consequently, you can now view sequential programming as hard-coding expected sequences of events. The simplest cases, like your blinky and button threads, hard-code only a single sequence of expected events repeated forever. The main advantages of sequential code is the simplicity of maintaining the context between events, because even though an RTOS can execute a lot of intervening code while a given thread blocks, each blocking call always returns to the exact point where it was originally called from. Therefore, the code following that blocking call can simply handle the event knowing that it must have arrived in the context of the hard-coded sequence. The main disadvantage of sequential code is that it is unresponsive to new events. Therefore, adding new events and new event sequences is hard. So while sequential programming is the simplest solution for sequential problems, like the original blinky or button threads, it does not scale well to real-life problems. This is because most real-life systems are not sequential, as they typically need to handle many possible event sequences. And this is why the event-driven paradigm has been invented. Event-driven programs can handle events in any order. Also, event-driven programs remain responsive to new events because all events are processed quickly without blocking. But the biggest problem of event-driven programming is how to preserve the context from one event to the next, because the dispatch operation loses all the context when it returns to the event loop. You saw an example of this problem with the blinky active object, where you had to invent the flag is LED on to remember the context of the timeout event. I will address this problem in the segment about state machines. And the final disadvantage of event-driven programming is that it necessarily requires an event-driven infrastructure based on inversion of control. Such an infrastructure is called a framework, And I suppose that the unavailability of lightweight, efficient, real-time embedded frameworks is one of the main reasons why event-driven programming is practiced so little in our field. But the real-time embedded framework for active objects doesn't need to be complex. In fact, you just saw how to build one with the FreeAct active object layer. At this point, you used a few services from the traditional FreeRTOS kernel, such as threads and message queues. But the traditional RTOS does not provide much else needed in event-driven programming, which you had to create yourself. At the same time, most mechanisms provided in a traditional RTOS are of no use in programming the event-driven active objects. Not only they are not helpful, they are outright harmful, because most of them are based on blocking, which is not allowed in event-driven systems. In the end, even though a traditional RTOS can be used to implement an event-driven framework, it is not the best fit. This should not be that surprising, because RTOS has been specifically designed to support the sequential programming paradigm. But an RTOS-based framework still makes sense in hybrid systems, where some functionality is implemented with traditional sequential threads, while other functionality is handled by event-driven active objects. You saw this in your first step of implementing active objects, when you had the button functionality implemented in an active object, but the blinking of the LED was still handled in a sequential thread. But a purely event-driven real-time embedded framework does not really need the blocking mechanisms. My experience from building such frameworks for the past 20 years shows that frameworks of that type can be significantly smaller and faster than a traditional RTOS, especially in the RAM footprint. This makes them ideal for single-chip microcontrollers.